Hi everybody, in this video we are going to combine math and equilibrium together. So how do we get from a situation not at equilibrium to a situation at equilibrium? Well, we know that when a reaction is not at equilibrium, it will move a certain direction depending on if Q is greater than or less than K. And it will do this until it reaches the perfect equilibrium between reactants and products. The reaction will lose or gain products in a stoichiometric manner, which means that it will be based on the reaction until it reaches the perfect concentrations, which are the concentrations that it wants at equilibrium. Now, we can predict the equilibrium conditions using an ICE table, where I stands for initial, C stands for the change in concentration or pressure, and etc. And E stands for the concentrations, pressures, and etc. at equilibrium. So before we begin, note that we can read reactions in terms of moles, molarity, and ATM. Cool, right? So now that we talked about that, let's actually do a practice problem. So here we have the conversion between H2 and I2 into 2HI, and they are at equilibrium. So it turns out that the Kp of this reaction is 50.0 at a constant temperature. So this constant temperature concept is very important. So I give you the starting pressures in a container. The partial pressure of H2 gas is 1.20 atmospheres, I2 is 0.333 atmospheres, and HI is 1.22 atmospheres. So these may or may not be at equilibrium, but in most cases, when I give you some pressures and I don't tell you if it's at equilibrium or not, it tends not to be at equilibrium. So I want the equilibrium partial pressures, or in other words, the pressures at equilibrium, as well as the total pressure of the container at equilibrium. So these three pressures are most likely not at equilibrium, and we'll find out by calculating the Q, or the reaction quotient. So step 1, figure out what direction the reaction will go to reach equilibrium. So to do that, we have to figure out if Q is greater than or less than K. So our Q is based on the reaction, so the partial pressure of HI squared over the partial pressure of H2 times the partial pressure of I2. And we substitute our values in. So notice how all these are in atmospheres, so we are good here, and we don't have to change anything. So 1.22 squared over 0.12 times 0.333 gives us 37.2. Now 37.2 is our Q, or our reaction quotient. Now you may notice that 37.2 is less than 50.0, so this means that Q is less than K, and when that's the case, we have too many reactants. So the reaction will proceed forwards to remove these reactants. So step 2, we gotta make an ICE table, and I'll show you how that works. But before we do that, let's write the reaction with a forward or backward arrow. So since we said this reaction proceeds forwards, we will use a forward arrow. So notice how I use a single arrow since the reaction is moving forwards and not at equilibrium yet. So since this reaction is moving forwards and not at equilibrium, we use a forward arrow instead of an equilibrium arrow. And this arrow will help us determine the signs for C, as you will see soon. So I is our initial pressures, and our initial partial pressures are here, here, and here, as indicated by the question where I give you the starting or the initial pressures. And what about the C? Well, for every X ATM of H2 that is used up, and for every X ATM of I2 that is consumed or used up, then 2X ATMs of HI is produced. And why is this? Well, if you read this reaction, you can think of it in terms of moles. For every 1 mole of H2 and I2 consumed, 2 moles of HI are produced. In the same way, for every 1 ATM of H2 and 1 ATM of I2 that is consumed, 2 ATMs of HI are produced. And remember, we can read reactions in terms of not only moles, but also atmospheres or even molarity. Now let's take a look at why I used X. Well, I don't know how much atmospheres of H2 or I2 that is going to be lost, so I put X there because that's a variable I want to know. So what about this negative sign? Well, if it's being consumed in the reaction, since this is a forward reaction where the reactants are leaving and the products are being produced, then this means that you have to use a negative sign for the reactants and a positive sign for the product since it is being produced. So the change in concentration or pressure will be positive because it is increasing since this reaction is a forward reaction. Now, E is the equilibrium partial pressures, and all you do is you take the initial and you add the change to get the equilibrium pressures. So if you combine I and C, you get that the equilibrium pressure for H2 gas is 0.120 minus X. For I2 gas, it's going to be 0.333 minus X. And for HI, it is going to be 1.22 plus 2X. And remember, we have to follow stoichiometry because for every one that is used up for each of these substances, 2 HI are produced. So there are twice as many. So you have to remember that. And we have these three nice equations, and we have to solve for X. So since these are all equilibrium pressures, we know that at equilibrium, the Kp is equal to 50.0 at a certain temperature, and this is equal to products over reactants. Now we do have the expressions for our products and reactants at equilibrium, so why don't we use those and plug them into our equilibrium expression? So the pressure of HI is here, the partial pressure of I2 is here, and the partial pressure of H2 is here. And notice how I squared the partial pressure of HI because it has a coefficient of 2 in the reaction. Now we set these two equal and we could substitute values and we get that 50.0 is equal to all this stuff. So notice how there's one variable and one equation. We can solve for X using algebra. So here is the equation we have to solve, and at first it looks very cumbersome. It looks complicated. And trust me, it is complicated. So let's do a lot of algebra. And before we continue, note that these numbers that I'm underlining right now are not exact numbers, and apparently all these have 3 sig figs. Meanwhile, our 2x, negative x, and negative x are exact numbers, meaning that they have an infinite number of sig figs, because according to the reaction, for exactly x moles of H2 or x atmospheres of H2 that is consumed, exactly twice as many moles or atmospheres of HI are produced. So these are exact numbers because this is stoichiometry, and stoichiometry tends to be exact. And because of that, they are exact numbers. So in this problem, I tried my very best to keep track of sig figs, and it's pretty tough, trust me. So the first thing I did was I kind of distributed this, and I got this. And we see that we distributed these two into a quadratic, and it continues down to here. And note that I underlined the 9 in order to keep track of sig figs, and in this case there are 3 sig figs in that number and not 4, but I kept the extra digit to be more precise, and to be more precise is better in many cases. Now I kind of just distributed the 50.0 and I got all this stuff, and remember the 4 right here is an exact number, so we don't worry about sig figs there. Now I move all of the terms on this side to that side by doing some subtraction, and I get that 0 is equal to all this. Notice how you can use something called the quadratic formula to solve for our x's. So the quadratic formula is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And note that the a is here, the b is here, and c is here. So we know that a is 46.0, b is negative 27.53, and c is going to be 0.51. And doing the math, all we do is we plug it in, and let's keep in mind our sig fig. So I simplified it very slowly. I first took the square of 27.53, or I mean negative 27.53 to get 758, and I multiplied these three terms out to get 93.8 with two sig figs, and I had to subtract them to get this. I took the square root, and I had two solutions for x, because you get one solution for adding this term, and you get one solution for subtracting this term, and that's why you have two solutions. But of course, in most cases, we will only need one of them, and that's because one of them will be wrong. So which one of these doesn't make sense? So let me change this, which one doesn't. So let me write doesn't. Alright, so I think that the one that doesn't make sense is 0.579, because according to the equation, our partial pressure of H2 at equilibrium would be 0.120 minus x. And remember, 0.120 minus x comes from here, and this is an expression telling us the equilibrium partial pressure of H2. So we have here 0.120 minus x, and if x is 0.579, we would get a negative partial pressure. So we can't have negative partial pressures because that's not a thing in chemistry. And because of that, the first x is non-applicable, so we toss that out and we keep the second. So x will be 0.0188. Now, assuming this is true, all we have to do to find the equilibrium partial pressures for each substance is substitute x for this number into each of the expressions to get the final or the equilibrium partial pressures. So this turns out to be the equilibrium partial pressures for every gas involved, and the total pressure is simply just adding up all three pressures, and you get that the pressure of the container is going to be 1.67 atmospheres. Now, do these equilibrium pressures actually make sense? Or in other words, are they truly at equilibrium? Well, you can easily check your answer by telling yourself, is 50.0 equal to this equilibrium expression when we plug in our equilibrium pressures? While doing the math, I get that 50.0 is about equal to 50.1, or approximately equal to 50.1. And it's off by 0.1 due to rounding error, but that's perfectly fine. So these two are equal, and this means that our pressures are truly at equilibrium, because when you put the pressures in, you get the equilibrium constant that is there at that temperature. So we checked our work by making sure that these pressures were in equilibrium. Now, before we end this video, I want to talk about other ways to solve these quadratic equations. So the first way to solve the quadratic equations, besides the quadratic formula, is by using some algebra tricks or simplifications if applicable. So for example, if I wanted to solve this, where 1 plus x times 1 plus x over 2 minus 2x squared is equal to k, I could simply combine these two terms, since they're the same term, and make it 1 plus x squared over 2 minus 2x squared and set that equal to k. But notice how they both share a 2 in common, so I can take the square root of both sides. So let's take the square root of both sides, and we get that 1 plus x over 2 minus 2x is equal to the square root of k. So notice how you can simplify things sometimes, but in our case, where we had this gigantic messy equation, you couldn't really simplify anything, and that's why we had to resort to the quadratic formula. Now, what are other ways that you could solve quadratic equations and find the zeros of them? Well, you could use a graphing calculator, and we could set 0 equal to the quadratic expression, such as what we did over here, and all we would do is we would simply graph y equals the quadratic expression we derived and find the x-intercepts, or when y equals 0, to get the x values that satisfy 0 equals the quadratic expression. So that should be expression and not equation. Now, there are other ways to solve it, and this is only if you have the right technology. So you could find an algebra solver, so some graphing calculators are able to solve algebraic equations. And sometimes you don't have that kind of technology, so there's something called the internet. And there's this cool site called Wolfram Alpha that can solve almost any equation you put into it. So it's a pretty cool website if you have access to the internet. And this website can solve very complicated quadratic equations, such as the one we started off here, in an instant, and it'll give you pretty accurate answers, even more so than the answers I gave, because they don't do much rounding. Their answers are pretty exact. So this program is amazing if you have the opportunity to use it. And that's all for this video. Have a nice day, everybody.